Introduction to NCC Gateway. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will explore NCC Gateway, a powerful spoke type within Google Cloud's Network Connectivity Center. NCC Gateway represents a significant advancement in how organizations secure their hybrid and multi-cloud network traffic. NCC Gateway is a regional product that enables security for cross-cloud network traffic. It allows you to enable security functions such as third-party security service edge, which is a cloud-delivered security component of secure access service edge architectures. Additionally, NCC Gateway can terminate interconnect connections, providing a unified approach to both connectivity and security. The key value proposition of NCC Gateway is that it provides streamlined integration with SSE partners. Rather than building complex network paths to route traffic through security appliances, NCC Gateway offers transparent steering for improved user-to-application protection and performance. This is particularly valuable for organizations adopting SASE frameworks where security needs to be applied consistently across all network paths. NCC Gateway supports regional deployment, meaning you can deploy it in various regions based on physical proximity to your data centers or other cloud providers. This geographic flexibility ensures optimal latency and performance for your security processing needs. NCC Gateway Architecture Overview. Let me explain the NCC Gateway architecture diagram that shows how all the components work together to deliver secure connectivity. The Network Connectivity Center Hub serves as the central orchestration point for all connectivity. This is a global resource that manages the routing between different spokes and ensures traffic flows correctly through your network. The NCC Gateway spoke is the regional component that attaches to the hub. This is where the magic happens. The gateway spoke is where traffic enters and exits the hub for security processing. All NCC Gateway spokes must be in a special spoke group called the Gateways Group, which is part of the hybrid inspection topology. Connected to the NCC Gateway is the cloud router, which must be in the same region as the gateway. The cloud router manages BGP sessions and route advertisements for the hybrid connections landing on the gateway. The VLAN attachments provide the physical connectivity to your on-premises networks through Cloud Interconnect. These attachments connect to the cloud router, and because the router is linked to the NCC Gateway, the traffic from these attachments flows through the gateway. The Secure Access Connect component links the NCC Gateway to your chosen SSE provider. This is the integration point where traffic gets sent to the third-party security service for inspection and policy enforcement. The SSE service represents your security service edge provider, such as Palo Alto Networks Prisma Access or Symantec Cloud SWG. This is where traffic is inspected, filtered, and secured before reaching its destination. Finally, the VPC's spokes represent your application workloads in Google CPVPC networks. These spokes connect to the hub and can route traffic through the gateway for security processing. Hybrid inspection topology explained. Let me walk you through the hybrid inspection topology diagram, which is the foundation for NCC Gateway deployments. The Network Connectivity Center Hub is the central component that orchestrates all connectivity. It is configured with the hybrid inspection preset topology, which creates the 4 required spoke groups automatically. The Gateway's spoke group is a special group that contains all network connectivity controller gateway spokes. This group is where traffic enters and exits for security processing. All gateway spokes in your hub must be members of this single Gateways group. The prod spoke group is designed for production workloads. VPC networks containing your production applications should be assigned to this group. Traffic between the prod group and the gateways group flows through SSE inspection. The non-prod spoke group is designed for non-production workloads such as development, testing, and staging environments. By separating non-prod from prod, You can apply different security policies or routing behaviors to these environments. The Services Spoke group is designed for services that are essential to both production and non-production workloads. This might include shared services like domain name system, logging, monitoring, or internal tooling that needs to be accessible from multiple environments. The arrows in the diagram show that Secure Sockets Layer Packet Inspection is available for traffic flowing between the Gateways group and each of the other three groups: prod, non-prod, and services. However, direct traffic between prod, non-prod, and services does not pass through Secure Sockets Layer Inspection. This architecture ensures that traffic crossing the security boundary is always inspected while allowing intra-group communication without unnecessary security processing overhead. Use case: branch users to Internet. Let me explain the traffic flow diagram for the branch users to Internet use case, which is one of the primary scenarios NCC Gateway addresses. The branch users represent employees or systems at your on-premises branch office location. These users need to access Internet resources securely, and you want to apply consistent security policies to their traffic. The traffic flows from the branch through the Cloud Interconnect VLAN attachment, which provides the physical connectivity between your on-premises network and Google Cloud. This is a dedicated or partner interconnect connection that lands on the NCC Gateway. The NCC Gateway receives the traffic from the VLAN attachment. Because this is branch to Internet traffic, the gateway routes it to the attached security service for inspection. The third-party SSE service inspects the traffic, applying security policies such as URI filtering, threat protection, and data loss prevention. The SSE service makes allow or block decisions based on your configured policies. For allowed traffic, the SSE service routes it to the Internet where it reaches the requested resources. The response traffic follows the reverse path, going through the SSE service for inspection before returning through the NCC Gateway and VLAN attachment to the branch users. This architecture ensures that all branch Internet traffic is secured through your secure service edge provider regardless of the destination. The branch users get consistent security protection as if they were connecting through a corporate data center, but with the performance benefits of Google Cloud's global network. Use case: private applications to Internet. Let me explain the traffic flow for the private applications to Internet use case, which secures outbound Internet traffic from your Google CP workloads. The private applications represent workloads running in your Google CP VPC's networks. These might be compute engine virtual machines, GKE containers, or other services that need to access Internet resources such as external APIs, software updates, or third-party services. When an application initiates an outbound connection, the traffic flows from the VPC spoke through the Network Connectivity Center Hub. The hub routes the traffic to the NCC Gateway because you have configured gateway advertised routes that direct Internet-bound traffic through the gateway. The NCC Gateway receives the traffic from the hub and routes it to the third-party SSE service for inspection. This ensures that all outbound Internet traffic from your workloads is subject to your security policies. The SSE service inspects the outbound traffic, applying policies such as Uniform Resource Locator filtering to prevent access to malicious sites, data loss prevention to protect sensitive data from leaving your network, and threat protection to block command and control communications. For approved traffic, the SSE service routes it to the Internet where it reaches the requested external resource. The response traffic follows the reverse path, flowing through the SSE for inspection before returning through the NCC Gateway and Hub to the VPC spoke. This architecture is valuable for organizations that need to enforce consistent egress security policies for their cloud workloads. By routing all Internet-bound traffic through the SSE, you gain visibility and control over what your applications are accessing externally. Processing capacity planning. Understanding processing capacity is critical for properly sizing your NCC Gateway deployment. The processing capacity of an NCC Gateway spoke is its provisioned bandwidth, and you must provision enough capacity to account for each traffic flow direction. A key concept to understand is that packets might enter and leave the gateway spoke more than once for each flow direction for some traffic flows. This is particularly important for use cases like branch to private applications where traffic passes through the gateway twice. Let me walk through the capacity calculation example shown. In the branch users to internet scenario, packets traverse the NCC gateway once in each direction. If you need 1 gigabits per second of full duplex bandwidth, meaning 1 gigabits per second from branch to internet and 1 gigabits per second from internet to branch, you need 2 gigabits per second of processing capacity. This accounts for both directions of traffic flow. The branch users to private applications scenario is more complex. Here, traffic passes through the gateway twice in each direction. From branch to application, traffic enters the gateway from the VLAN attachment, then exits the gateway toward the hub. From application to branch, traffic enters the gateway from the hub, then exits toward the VLAN attachment. If you need 1 gigabits per second of full duplex bandwidth between branch and applications, you need 4 gigabits per second of processing capacity, 2 gigabits per second for branch to application traffic passing through twice, and 2 gigabits per second for application to branch traffic passing through twice. The supported capacity values for NCC Gateway spokes are 1, 10, or 100 gigabits per second. Choose the appropriate value based on your calculated requirements. You can change the processing capacity later if needed, but it is best to plan appropriately from the start. Also note that if your SSE partner recommends higher bandwidth than your calculations indicate, you should follow the partner's recommendation. NCC Gateway Setup Overview. Now that we understand the concepts behind NCC Gateway, let us walk through the complete setup process. Setting up NCC Gateway involves several sequential tasks that must be completed in the correct order. The setup workflow diagram shows the 5 main steps you need to follow. First, you create a Network Connectivity Center hub with the hybrid inspection topology. This hub will be the central orchestration point for all your connectivity. Second, you connect VPC networks to the hub as spokes. These VPC spokes represent your application workloads and must be assigned to the appropriate spoke groups based on the hybrid inspection topology. Third, you create the NCC Gateway spoke itself. This regional resource attaches to the hub and provides the security processing capabilities. Fourth, you connect the Secure Access Connect attachment to the NCC Gateway. This step establishes the integration with your chosen SSE provider. Fifth, you add hybrid connections by creating cloud routers and VLAN attachments that land on the NCC Gateway. This provides connectivity to your on-premises LANs. After completing these 5 steps, you can optionally create gateway advertised routes to control how traffic is directed through the gateway. You can also repeat steps 3 through 5 to add NCC Gateway spokes in additional regions if needed. Enabling the Network Connectivity API. The first technical step in setting up NCC Gateway is enabling the Network Connectivity API. This API must be enabled before you can create any Network Connectivity Center resources. Let me walk through the command shown. The G-Cloud Services Enable command is used to enable Google Cloud APIs in your project. The Network Connectivity.googleapis.com parameter specifies which API to enable, in this case the Network Connectivity API. You can also enable this API through the GCP console. Navigate to the Network Connectivity Center page and click Enable when prompted. Alternatively, use the API library in the console to search for and enable the Network Connectivity API. After enabling the API, you should verify it is active by listing the enabled services. The G-Cloud Services List command with the enabled filter shows all APIs currently enabled in your project. Look for networkconnectivity.googleapis.com in the output to confirm successful enablement. If you are working with multiple projects, ensure you have set the correct project before enabling the API. Use G-Cloud config set project followed by your project ID to switch projects. You can verify your current project with G-Cloud config list. The network connectivity API enablement is typically instantaneous, but in some cases it may take a few minutes to propagate. If you encounter permission errors immediately after enabling, wait a moment and retry your operation. Creating the hub command breakdown. Let me provide a detailed breakdown of the hub creation command and API request so you understand each component. In the G-Cloud command, the G-Cloud beta prefix indicates we are using beta features. The network connectivity hubs create subcommand specifies we are creating a new hub resource. The hub name placeholder should be replaced with your chosen hub name. Hub names must be unique within your project and should follow Google Cloud naming conventions. Lowercase letters, numbers, and hyphens only, starting with a letter. The preset topology equal operator hybrid inspection parameter is mandatory for NCC Gateway support. This preset automatically creates the 4 spoke groups and configures the routing policies between them. You cannot change the topology after hub creation, so ensure you select hybrid inspection if you plan to use NCC Gateway. In the API request, the project ID in the URL path identifies your Google CP project. The location/global segment indicates that hubs are global resources, not regional. The request body contains the hub configuration as a JSON object. The name field specifies the hub ID. The description field is optional but recommended for documentation purposes. The labels field accepts key value pairs for organizing and filtering resources. The preset topology field must be set to hybrid inspection in uppercase for the API. After hub creation succeeds, the API returns the hub resource with additional fields including the creation timestamp, state, and unique URI. Store the hub URI as you will reference it when creating spokes. VPC Spoke Group Assignment. Understanding spoke group assignment is essential for proper network segmentation and security policy enforcement in the hybrid inspection topology. The diagram illustrates how VPC networks should be assigned to spoke groups based on their purpose. The prod group contains production workload VPCs. These are networks hosting your live, customer-facing applications and services that require the highest level of security and availability. The non-prod group contains non-production workload VPCs. These networks host development, testing, staging, and other pre-production environments. Separating non-prod from prod ensures that development activities cannot impact production systems. The services group contains shared services VPCs. These networks host services that both production and non-production environments need to access, such as DNS servers, logging infrastructure, monitoring systems, or internal tooling platforms. The Gateways group is reserved exclusively for NCC Gateway spokes. You cannot assign VPCs spokes to this group. The Gateway spokes in this group provide the security processing for traffic flowing between on-premises networks and the other spoke groups. Remember that secure sockets layer packet inspection only occurs for traffic between the Gateways group and the other 3 groups. Traffic flowing directly between prod, non-prod, and services does not pass through secure sockets layer inspection. Plan your network segmentation accordingly to ensure traffic that requires security inspection is routed through the gateway. A spoke can only belong to one group, and you cannot change the group assignment after spoke creation. If you need to move a VPC to a different group, you must delete the spoke and recreate it with the new group assignment. Gateway Spoke Parameters Deep Dive. Let me provide additional detail on the Gateway Spoke parameters to help you make the right configuration choices. For the region parameter, consider these factors when selecting where to deploy your gateway. Choose regions close to your cloud interconnect attachment locations to minimize latency for on-premises traffic. If you have users or branches in multiple geographic areas, you may need gateway spokes in multiple regions. Each region can have only one gateway spoke per hub. For the capacity parameter, The 3 tiers offer flexibility based on your needs. The 1 gigabits per second tier is suitable for smaller deployments or proof of concept environments. The 10 gigabits per second tier handles most enterprise workloads with moderate traffic volumes. The 100 gigabits per second tier supports high bandwidth environments with heavy traffic requirements. Remember that capacity calculations should account for traffic patterns, and branch to private app scenarios require 4 times the actual bandwidth due to double pass through the gateway. For the IP range reservations, the /23 block provides 512 IP addresses for gateway infrastructure. Choose a range from your organization's private IP space that is not used elsewhere. Document this allocation to prevent future conflicts. Common choices include ranges like 10.2, 5.0.0/23 or 172.16.100.0/23 that are clearly separated from your workload subnets. Some IP ranges are reserved for SSE partners and cannot be used for your gateway. If you receive an error about overlapping ranges, try a different /23 block. After creating the gateway spoke, verify it is in the active state before proceeding. Use G-Cloud Network Connectivity spokes described with the spoke name and region to check the status. Connecting Secure Access Connect to NCC Gateway. The next step is connecting the Secure Access Connect attachment to your NCC Gateway. This integration enables traffic to flow to your chosen SSE provider for security inspection. Secure Access Connect is the service that establishes connectivity between NCC Gateway and third-party SSE products. It handles the tunnel establishment, routing, and traffic steering to send packets to the SSE service and read inspected traffic back. The connection process varies depending on your secure service edge provider. For Palo Alto Networks Prisma Access, you configure the integration through the Prisma Access Management Console and the Secure Access Connect interface in Google CP. For Symantec Cloud SWG, you follow the Symantec-specific configuration workflow. Before connecting, ensure you have the necessary permissions. You need network connectivity.spokes.use permission on the NCC Gateway resource and network security.sac attachments.update permission on the Secure Access Connect attachment resource. Only one service can be attached to an NCC Gateway at a time. If you need to change secure sockets layer providers, you must disconnect the current service before connecting a new one. The detailed configuration steps are documented in the Secure Access Connect documentation and vary by provider. The key outcome is that after this step, traffic routed through the NCC Gateway will be sent to your SSE service for inspection before reaching its destination. Verify the connection is active by checking the Secure Access Connect attachment status in the console or via the API. The attachment should show as connected with the SSE service details visible. Adding hybrid connections overview. With the NCC Gateway spoke created and Secure Access Connect configured, the next step is adding hybrid connections. These connections provide the physical connectivity path between your on-premises networks and the NCC Gateway. Hybrid connections for NCC Gateway consist of 2 main components: Cloud Router and VLAN attachments. The Cloud Router manages BGP sessions and route advertisements, while VLAN attachments provide the Layer 2 connectivity through Cloud Interconnect. The diagram shows how these components relate to each other. The NCC Gateway spoke attaches to the hub. The Cloud Router links to the NCC Gateway in the same region. VLAN attachments connect to the Cloud Router and provide paths to your on-premises network through Cloud Interconnect. There are important constraints to understand. The Cloud Router must be associated with an NCC Gateway in the same region. Only VLAN attachments created with a Cloud Router linked to an NCC Gateway become part of the Gateway spoke. You cannot attach Cloud VPN tunnels or router appliances to NCC Gateway spokes. Only VLAN attachments are supported. For high availability and to meet Cloud Interconnect SLA requirements, you should create redundant VLAN attachments. This typically means two attachments using separate interconnect connections or separate edge availability domains. The traffic from these VLAN attachments flows through the NCC Gateway before reaching the hub, ensuring all on-premises traffic is subject to SSE inspection. Cloud Router Configuration Parameters. Let me explain the optional parameters available when creating a cloud router for NCC Gateway. The BGP identifier range parameter specifies an IP version 4 address range that serves as a unique identifier for the cloud router. This is useful when you have multiple cloud routers and need to distinguish their BGP sessions. The range should be a /30 or larger block from a private IP range. The Keep Alive interval parameter sets the BGP Keep Alive timer in seconds. Valid values range from 20 to 60 seconds. The default is 20 seconds. A shorter interval detects failures faster but generates more BGP traffic. A longer interval reduces traffic but increases failover time. Choose based on your availability requirements and network characteristics. For the advertised routes configuration, you have flexibility in what routes to advertise. The advertisement mode can be default to advertise all subnet routes automatically, or custom to explicitly control advertisements. With custom mode, you specify ranges using set advertisement ranges. When using custom advertisements, consider which RAS your on-premises network needs to reach resources in Google CP. This typically includes VPC subnet ranges, but you might also advertise specific service IP ranges or summarized prefixes to reduce the number of RAS. After creating the cloud router, you cannot change the NCC Gateway linkage. If you need to associate the router with a different gateway, you must delete and recreate the router. However, you can modify the custom route advertisements at any time. Configuring BGP sessions. After creating the cloud router and VLAN attachments, you need to configure BGP sessions to establish routing between your on-premises network and Google Cloud. BGP sessions run between the cloud router and your on-premises router over each VLAN attachment. You configure a BGP peer on the cloud router that corresponds to your on-premises router's BGP configuration. The sequence diagram shows the BGP establishment process. Your on-premises router and the cloud router exchange BGP open messages to establish the session. They then exchange update messages containing route advertisements. The cloud router advertises the routes you configured, while your on-premises router advertises routes to your branch networks. For each VLAN attachment, you create an interface on the cloud router and then add a BGP peer configuration. The interface specifies the IP addressing for the cloud router side of the BGP session. The peer configuration includes your on-premises router's IP address and ASN. Important BGP configuration parameters include the peer ASN, which must match your on-premises router's ASN. The peer IP address is the on-premises router's interface IP on the VLAN. The advertised route priority affects path selection when you have multiple attachments. When both BGP sessions are established and routes are exchanged, traffic can flow between on-premises and Google Cloud through the NCC Gateway. The gateway ensures all traffic passes through SSE inspection before reaching its destination. Understanding gateway advertised routes. Let me explain how gateway advertised routes work within the Network Connectivity Center architecture. When you create a gateway advertised route, it is installed in the route table of the hub to which the gateway spoke is connected. The NCC Gateway itself becomes the next hop for packets matching this route's destination. The diagram illustrates the route flow. VPC spokes in the hub see the gateway advertised route in their routing decisions. When a packet's destination matches the route, it is sent through the hub to the NCC Gateway. The gateway then processes the traffic through the SSE service. Gateway advertised routes follow standard best path selection mode for determining route priority. The effective Andromeda route priority is calculated based on the priority you specify when creating the route. The actual priority in the hub ROT table will be values like 65536 or 65537. An important consideration is that static ROTs always have priority between 0 and 65535, which takes precedence over gateway advertised ROTs. If you want to direct internet traffic to the gateway using a quad 0/0 advertised ROT, you might need to remove the system-generated default ROT from your VPC networks. Gateway advertised ROTs do not appear in the VPC ROT table directly. You can read them in the Hub ROT table of the Spoke group. Use the G-Cloud Network Connectivity Hub's ROT tables ROTs list command to see all ROTs including gateway advertised ROTs. Important considerations and limitations. Before completing your NCC Gateway deployment, it is important to understand the key considerations and limitations that affect how you design and operate your network. NCC Gateway supports SSE service insertion only. This means traffic can be steered to third-party SSE providers, but other types of network functions or services cannot be inserted at this time. Only VLAN attachments can connect to NCC Gateway spokes. Cloud VPN tunnels and router appliances are not supported for gateway hybrid connections. If you need VPN connectivity, you must use a separate hybrid spoke configuration. All NCC Gateway spokes must be in the Gateway's spoke group. The hybrid inspection topology enforces this requirement, and you cannot place Gateway spokes in other groups. Only one service can be attached to an NCC Gateway at a time. You cannot chain multiple SSE services through a single gateway. If you need multiple security services, you must implement them within your chosen SSE provider's platform. You can only have one NCC Gateway spoke per region per hub. If you need gateway capacity in multiple regions, create additional gateway spokes in those regions. The gateway spoke and hub must be in the same project. Cross-project gateway deployments are not supported. IP address ranges assigned to the gateway cannot be changed after creation. Plan your IP allocation carefully before creating the gateway spoke. There is no traffic steering policy to bypass a subset of traffic from the NCC Gateway. All traffic matching gateway advertised ROTs will pass through the gateway. Viewing Hub ROT tables. Understanding how to view and interpret Hub ROT tables is essential for troubleshooting and verifying your NCC Gateway deployment. The Hub ROT table shows all ROTs available within the Network Connectivity Center Hub, including ROTs from VPC spokes, hybrid spokes, and gateway advertised ROTs. Each spoke group has its own view of the ROT table. The G-Cloud command to read Hub ROT tables is G-Cloud Network Connectivity Hub's ROT tables ROTs list. You specify the hub name, the ROT table name which corresponds to a spoke group, and optionally filter by region or other criteria. When you query the ROT table, you can specify a region to see the effective ROTs from that region's perspective. This accounts for inter-region costs when selecting ROTs. It shows which particular gateway instance would receive traffic if you send a packet from that region. The output shows ROT entries with their destination CIDR, next hop, state, and type. Gateway advertised ROTs appear with the gateway spoke as the next hop. VPC spoke ROTs show the VPC network as the next hop. For troubleshooting, compare the ROTs you expect to read with what appears in the ROT table. If a gateway advertised ROT is missing, verify the ROT was created successfully and is in the open state. If traffic is not flowing as expected, check that the ROT priority is appropriate relative to other ROTs for the same destination. Remember that gateway advertised ROTs do not appear in VPC ROT tables. Always check the Hub ROT table when troubleshooting gateway routing issues. Use case: mobile users to Internet. Let me explain an important use case supported by SSE partners: mobile users accessing the Internet. This scenario differs from the branch user cases because traffic does not flow through the NCC Gateway. Mobile users are remote employees connecting from laptops, tablets, or smartphones outside your corporate network. These users need secure internet access with consistent security policies regardless of their physical location. In the traffic flow diagram, mobile users connect directly to the SSE service. The SSE provider's client software on the user's device establishes a secure tunnel to the nearest SSE point of presence. This connection happens over the public internet without traversing Google Cloud infrastructure. The SSE service inspects the mobile user's internet traffic and applies security policies. This includes URL filtering to block malicious or policy-violating sites, threat protection to detect malware and phishing attempts, and data loss prevention to protect sensitive information. After inspection and policy enforcement, approved traffic is forwarded to the internet. The response follows the reverse path through the SSE service back to the mobile user. This use case is entirely handled by the SSE partner's infrastructure. The NCC Gateway is not involved because the mobile user is not connecting through your on-premises network or cloud interconnect. However, this use case complements NCC Gateway by providing consistent security for your entire workforce, whether they are in branch offices connecting through the gateway or working remotely as mobile users. Use case: branch users to partner applications. Some SSE partners offer the ability for branch users to access partner-hosted applications. Let me explain this traffic flow pattern. Partner applications are services hosted by the SSE provider or within their partner ecosystem. These might include security dashboards, management consoles, threat intelligence feeds, or other value-added services that complement the core SSE functionality. In this traffic flow, branch users initiate a connection to a partner application. The traffic flows from the branch through the Cloud Interconnect VLAN attachment to the NCC Gateway. The NCC Gateway forwards the traffic to the SSE service through Secure Access Connect. The SSE service recognizes that the destination is a partner application and routes the traffic accordingly within the SSE provider's infrastructure. The partner application processes the request and sends a response. The response follows the reverse path through the Secure Sockets Layer service to the NCC Gateway, then through the VLAN attachment back to the branch users. Notice that in this flow, traffic passes through the NCC Gateway twice in each direction, similar to the branch to private applications use case. This is important for capacity planning. Not all Secure Service Edge partners support this use case. Check with your chosen Secure Service Edge provider to confirm whether partner application access is available and which specific applications are accessible through this mechanism. Multi-region deployment architecture. For organizations with geographically distributed users and resources, NCC Gateway supports multi-region deployment. Let me explain the architecture and considerations. The diagram shows a hub with NCC Gateway spokes in two regions, US Central and Europe West. Each gateway spoke has its own cloud router, VLAN attachments, and Secure Access Connect integration. VPC spokes connect to the hub globally. When a VPC resource sends traffic that matches a gateway advertised route, the hub routes it to the nearest gateway based on the effective route priority. This priority takes into account inter-region costs. On-premises locations connect through the gateway in their closest region. Branch offices in North America would connect through the US Central Gateway, while European branches connect through the Europe West Gateway. Each regional gateway can have different capacity configurations based on the traffic volume expected in that region. You might deploy a 10 gigabits per second gateway in your primary region and a 1 gigabits per second gateway in a secondary region with lower traffic. The SSE integration in each region connects to the SSE provider's nearest point of presence. This minimizes latency for security processing by keeping traffic geographically close to users. To add a new region, repeat the gateway spoke creation, cloud router configuration, VLAN attachment setup, and Secure Access Connect integration for the new region. Each region operates independently while sharing the same hub for centralized management. Best practices for NCC Gateway deployment. Based on the deployment patterns and considerations we have covered, let me summarize the best practices for NCC Gateway deployment. First, plan your capacity carefully. Calculate the required processing capacity based on your traffic patterns, accounting for double pass scenarios in branch to private application use cases. Start with adequate capacity and monitor utilization to adjust as needed. Second, design for high availability. Deploy redundant VLAN attachments using separate interconnect connections. For critical deployments, consider multi-region gateway deployment to provide failover capabilities. Third, organize your spokes logically. Use the prod, non-prod, and services groups thoughtfully to implement network segmentation. Place workloads in the appropriate group based on their security requirements and access patterns. Fourth, document your IP allocation. The gateway's /23 IP range and your advertised routes should be carefully documented to prevent conflicts and simplify troubleshooting. Fifth, establish monitoring and alerting early. Configure dashboards and alerts before going into production so you can quickly identify and respond to issues. Sixth, coordinate with your SSE provider. Work closely with your Prisma Access or Symantec Cloud SWG team to ensure the integration is configured correctly and security policies align with your requirements. Finally, test thoroughly before production deployment. Validate all traffic flows, verify security policy enforcement, and confirm failover behavior under various failure scenarios. Security considerations. Deploying NCC Gateway involves important security considerations beyond the SSE traffic inspection. Let me highlight key areas to address in your security planning. First, protect your NCC Gateway configuration with appropriate IAM controls. Limit who can create, modify, or delete gateway spokes, advertised routes, and cloud router configurations. Use custom IAM roles to implement least privilege access. Second, secure your cloud interconnect connections. The VLAN attachments connecting your on-premises network to the gateway should use appropriate encryption if your security requirements mandate it. Consider MAC-SEC encryption for dedicated interconnect connections. Third, implement network segmentation using the spoke groups effectively. Use the prod, non-prod, and services groups to isolate workloads with different security requirements. Remember that traffic between these groups does not pass through SSE inspection unless it goes through the gateway. Fourth, monitor for security events across the entire traffic path. Combine secure sockets layer security logs with cloud audit logs and VPC flow logs for comprehensive visibility into network activity. Fifth, maintain your secure sockets layer policies actively. Regularly review and update security policies in your Secure Service Edge Providers console to address emerging threats and changing business requirements. Sixth, plan for incident response. Document procedures for responding to security incidents involving gateway traffic. Include steps for isolating compromised networks, collecting forensic data, and coordinating with your SSE provider. Summary and next steps. We have covered the complete NCC Gateway technology, from concepts through deployment and operations. Let me summarize the key points and suggest next steps for your implementation. NCC Gateway is a regional spoke type that enables security for cross-cloud network traffic through integration with third-party SSE providers. It uses the hybrid inspection topology with 4 spoke groups: gateways, prod, non-prod, and services. The setup process involves creating a hub with hybrid inspection topology, connecting VPC's networks as spokes, creating the gateway spoke, integrating secure access connect with your SSE provider, and adding hybrid connections through cloud router and VLAN attachments. Key use cases include branch users to internet, branch users to private applications to internet, and partner-specific scenarios like mobile user access. For next steps, I recommend starting with a proof of concept deployment in a non-production environment. This lets you validate the configuration, test traffic flows, and familiarize your team with operations before production deployment. Review the Network Connectivity Center documentation for the latest features and updates. Engage with your secure service edge provider early to plan the Secure Access Connect integration. Consider your long-term architecture needs, including multi-region deployment for geographic coverage and capacity requirements for growth. Thank you for your attendance. Please consider subscribing to the channel and liking this video.